Everyone, welcome back to a new video. Today we're looking at LeetCode 1315. It's called Sum of Nodes with Even Valued Grandparent. So in the description we're told that we're given the root of a binary tree, and notice that it's not a perfect binary tree, and we can see that in the example down here. Many of the nodes don't have two children. And we're asked to return the sum of values of nodes with an even valued grandparent. And if there are no nodes with an even valued grandparent, then we need to return 0. Okay. And we're told the definition of a grandparent, which hopefully is intuitive. If you've ever worked with binary trees, you understand the concept of a parent node. A grandparent node is just the parent of a parent. We can take a look at this example. The coloring's a little confusing here. They've got a description down here. Basically, every red node here has a grandparent that is even valued, but which ones have which is you have to do some investigation. So the grandparents for 2 and 7, or the grandparent for 2 and 7 that is even, is 6, and same thing for 1 and 3, whereas 5 has a grandparent of 8 that's even, and so that's why it's red. Visually, when you inspect these, the only place that it's possible for this node right here, all these nodes on this level to have an even valued grandparent is 2 levels up, so it can only be the root. But as we go farther down the tree, there are more possibilities. So, there's 5, its grandparent is 8. You can imagine as this gets deeper and deeper and deeper, there could be ways for grandparents to exist higher up in the tree. Okay, so to me, this is a classic depth-first search solution problem. Again, you could, like with any of these tree methods, depth versus breadth, it's kind of down to personal choice and problem design. I think DFS, depth-first search, is going to work really well here. So I'm going to go ahead and get into it. So for our DFS function, we need a couple different things. We need to get the current node wherever we are in the function so we can get those values, right? Because we've got to sum all those values up. And then we need some context of hierarchy. So we need to know where the grandparent is, and then we also need to know where the parent is. And the reason we need to know where the parent is that as we work down the tree, it's possible for each parent to then become a grandparent, depending on the depth of the tree. So let's just write some pseudocode here. I think I've got the inputs right. So we're going to need access to our current node. And of course, we need a definition right here. So define DFS. We need to track our current node, we need to track the parent of our current node, and then we need to track the grandparent. Don't worry about how we're going to initialize these just yet. Just know that we need them. And then with DFS, we generally need 3 things. We need a base case. We need to do something. We have a do something and also a conditional. So we need to check if grandparent is odd. Well, we can check if it's even. That's probably a little better. And then if so, we want to do something. We want to sum things up. And then finally, we have to recurse. We have to move the function forward so that we get to a terminal state. And then, just so I remember, because it's kind of easy to forget, you can write the function and forget to call it. We need to call DFS. And then we need to return our solution value, whatever that's going to be. All right, so what's our base case? Well, in general, with depth-first search, with these binary trees, we just need to make sure that the node that we're interested in isn't null. So what we can do is we can say, if not current, then we can return none. And then down here, we've, in our code comments, in our pseudocode, I've really almost written the logic that we need to do here, we can basically say if grand and basically grand is even, so grand modulus 0, I'm sorry, grand modulus 2 is equal to 0, then we can do something. Now, I have a mistake here. We need the value from grand. Modulus on a tree node type is not going to get us anything. It's going to get us an error is what it's going to get us. Now, at our do something step here, this is a little trickier. Because what is it we want to do? We want to add to our total value that we're trying to return, or solution value. So in this example problem, we need to get the value of 18. It's interesting how we want to track that, because notice I don't have it set up in the function call, so we're not going to pass that value around. And it would be hard to do so because we could have branches that don't have access to that value. So I think the easiest way to store this is actually going to be a Python dictionary. So we can call our dictionary solution, so that I have to change less code below, and we can have an answer value that's initialized as 0. And then I can update this real quick before I forget. And then we can get back to our do something loop down here. If you're wondering why I'm choosing a dictionary here, we could use just a generic variable. Like we could just say, solution. So we could say solution is equal to the current value plus itself. The issue we're going to run into here, remember this is not a dictionary, pretend this is like an integer or something. We initialize solution up here as 0 or something like that. The issue we run into is we have a local variable defined too early, basically. And so we would need to do a global call up here, and that will work. But I've had issues before, actually, with LeetCode's environment and calling global variables from local scope. And so to avoid issues, I think this is probably our safest solution. So instead of calling this make-believe variable that we don't have, I'm going to say answer in solution is equal to answer in solution plus the current value. And I think that covers our do something logic. And then finally, we just have to think about how do we want to recurse. And really, this just means we need to move down the left and right children of our current node. But the tricky thing is that we need to age, in a sense, our nodes up here. What do I mean by that? I mean, so when we call DFS, we need to have the next current value, its parent, and its grandparent. And the way we do that is we call current and we move down its left side first. And then when we do that, whatever was current and is current in this function call will now become the parent value. That's in that position for the argument. And then what was the parent can now become the grandparent. And we can do that also on the right side as well. So that covers our recursion. And then finally, we just need to think about how we need to call this function, which is a little tricky actually, because it might be tempting to try to find a way to start at the only level where this could be valid, meaning there's no way on the first or second level, or the 0th or first level, depending on how you want to define the level of this tree, there's no way that we could get a value. There's no way that we could have any sum. There's no way that we could alter the solution variable, the solution dictionary with the answer variable. And the reason we couldn't do that is because no grandparents exist. So it might be tempting to try to just get down to this level and start the function off there. But what is actually easier and more efficient for us is that we can call in root as the current value, and then it's true that root has no parent and it has no grandparent. And so what will happen is, as we go to the first level of this tree, we'll pass the current check, but we won't pass the grandparent check. And it won't be until we get to this second level down here that the grandparent check, the first half of this if statement has a chance to pass. Okay, let's run this and see if we have any syntax errors. Very cool. Okay, so that passed, and yeah, let's run it through all of the solutions and see if we get anything wrong here. Okay, so I've run the code now through all of the different test cases, and we definitely passed. The runtime's really good. The memory management is not as good. I'm not really sure exactly what we would need to do to get over here. It may be that using decks and queues with a breadth first search solution would be a little more memory efficient, but the runtime's really good, and this is the same code we all wrote together. Even with the code comments saying, hey, maybe if I take those out, the memory would be a little better. I don't think it will be, but I don't know. If I get desperate, maybe I'll try that. Anyway, I hope you enjoyed the video. I hope you learned something, and let's tackle a new problem together real soon.